Welcome to the course on fundamentals of Mimo wireless communications. We have seen the expression of mutual information, and we have also tried to understand the intuitive meaning of why that particular expression yields the expression of capacity. So what we have last discussed is capacity can be expressed in terms of maximization of mutual information between the source and the destination over all possible distributions at the source. So with that, we move forward towards waveform channels, and we would be interested in looking at the Gaussian channel, so as to get the expression which is most commonly known, and using that or equipped with all these things, we will be able to easily understand the expression of typically flat frequency flat Mimo channel. So let us begin our discussion with that. So if we take the Gaussian channel, so for the Gaussian channel, we have the source which generates symbols xi, and these symbols go through the channel where zi noise gets added, and what is received is yi. And this noise zi, we will say they are distributed according to normal distribution with 0 mean and a certain noise power, so which you can write it as n or n naught or n noise. And we also have the constraint that if a code word is designed in a way that is a sequence of symbols xn which is transmitted, we have the constraint that 1 upon n I equals to 1 to n xi squared is less than or equal to p. So this is basically a power constraint. This is very important, because most of the communication systems that we deal with, they have some constraints, and these constraints, amongst many constraints, one of the most commonly understood constraint is a power constraint. That means there is limited amount of power available at the transmitter. There can be many kinds of power constraints. One of the most common power constraint is the average power constraint. So what we are considering over here is average power constraint written in a particular form. So moving forward, so this is the expression, this is the one which constrains the power, and if we have to find the capacity or the information theoretic capacity of this channel, we would write C as max I xy. So this is, we had explained, over p of x such that E x squared is less than or equal to p. So given this constraint over all possible distributions, you have to maximize the capacity. Now if we consider a Bpsk channel, we will just digress a little bit. If we consider a Bpsk modulation, so this is, let us say, minus S1, and this is plus S1 or plus A and minus A. If we consider plus minus A and plus A, when signal is transmitted, when A is transmitted, the probability of the received signal can be, or PDF can be drawn in this way because of noise. When minus A is transmitted, the PDF of the received amplitude can be drawn in this manner. And if we consider A has been transmitted and find the area under this curve, we are going to get the probability of error when plus A is transmitted. Similarly, when minus A is transmitted, we could find the area under this tail, and we could find what is the error probability. So basically what we can calculate is a probability of error under this condition. So if we would be able to calculate a probability of error, then we can say that, suppose if this is 0 and this is 1, if a 0 is sent with a probability of error, it becomes a 1, or rather with a probability of error Pe, it becomes 1, and with 1 minus P it remains 0. If a 1 is sent, it goes to 1, and 0, it goes to 0 with probability P, and with 1 minus P it becomes 1. So basically a waveform channel can be converted to a binary symmetric channel or vice versa. So this is just to keep in our mind, so that when we are translating from discrete to waveform channels, we can easily do in this particular fashion. So coming back to our expression over here, if we would write the expression of I xy, what we get is h of y minus of h y given x. So this expression is what we had derived earlier as the expression of capacity. So h of y minus h of y given x, basically yi, as we have over here, is xi plus zi. So basically minus h of x plus z conditioned on x. H of x conditioned on x is 0. So basically it is h of z conditioned on x. So z, that is noise, is independent of the source. So basically h of z conditioned on x is basically h of z. So all we said is x conditioned on x is 0, h of z conditioned on x is basically h of z, because these two are independent. And h of z, as we all know, in case of real constraint, we are going to have this as log base 2 pi e n. N is the power of the noise component. So this is what we have derived, the entropy of Gaussian a Gaussian distribution, the differential entropy of a Gaussian distribution. All we have to do is to now calculate this. So if we look at E of y squared, that means the variance or the power of y squared, we could write it as E of x plus z squared, which is E of x squared plus E of z squared plus 2 ex times Ez. Now E of x is 0, it is a 0 mean symbol. E of z is 0 because it is additive white Gaussian noise with 0 mean. So we are left with Ex squared plus Ez squared. So Ex squared we could restrict it to p, and Ez squared is n. So basically E of y squared is p plus n, or this is the variance of y, you can say. So if we have to calculate h of y, we could say that it is less than or equal to half log 2 pi e p plus n. So we have this term now, we have this term now, so we have to calculate this. So I of x y would be half log 2 pi e p plus n minus half log 2 pi e of n. So if you work it out, it becomes half log p plus n upon n, or half log 1 plus p by n. This is the well known expression for the capacity of a Gaussian channel. So if we move further beyond this and look at the situation when we have a complex Gaussian, so again in that case we have yi equals to xi plus zi, and in this case we would say that okay, zi is Gaussian, complex Gaussian distributed. In that case again these expressions do not change, this expression remain the same. So here simply we would be writing log determinant of pi e determinant of p plus n minus log pi e of n. Rather, determinant is not there, pi e p plus n, because you would remember in the other case we had root 2 pi e to the power of n, and in the other case it was pi e to the power of n, and here in the real case it was k determinant of k to the power of half, and here it was determinant of k. So by virtue of that you get log p plus n upon n, which is equal to log of 1 plus p upon n. So when you have complex, the expression would look like this, which is a well known expression for capacity which we are using for Gaussian channel. So that means whatever we have discussed does easily lead us to the expression of capacity for a Gaussian channel. That is what we have just now seen. Now since we have seen what is the result for a seesaw channel, now we will be moving on to finding the expression of capacity for a Mimo channel. So as we move forward, we have now almost reached our goal. That means we want to find the capacity of frequency flat. We are saying deterministic. I will explain the reason why. So we are finding the capacity. We understand the expression of we understand the meaning of capacity, that is maximization of mutual information over all possible source distributions. We have given an intuitive meaning of it. When we talk about frequency flat, we understand what is frequency flat. We have described in details what leads to frequency flat. When we say deterministic, that means it is given for a particular realization of a channel. We know what are the details of Mimo channel. So only deterministic word is new in this case, and all we are trying to say is it is known. Later on we will see when a channel is a random channel what happens because of that. So, in this Mimo configuration, we have MT transmit antennas, we have MR receive antennas, and let our channel bandwidth be 1 Hertz. Okay, for simplicity or for ease, you can always multiply by the bandwidth to get it, and it is assumed it is frequency flat over this band. Okay. Further, we have always written capital H indicating the channel transfer matrix of size MR cross MT. So, we could write received signal Y, which is a vector, MR cross 1 being equal to root over ES upon MT. When I write root over ES by MT, this clearly means that the signal power is divided equally amongst MT transmit antennas at this stage. Later on, this will get modified. Times H as a matrix indicated by a double underline. S is the vector MT cross 1, this is MR cross MT, plus, if this is noise, MR cross 1. So, this equation fits in MR. So, basically MR number of noise samples corresponding to MR receive antennas, MT number of symbols, and this is MR cross MT channel matrix, and this is MR number of received antennas. So, basically it is redundant to draw this picture 1 to MT and again 1 to MR number of receive antennas. S1 up to SMT is getting transmitted, Y1 up to YMR is getting received. Okay. So, this is the system model, and ES is the total average energy at the transmitter over a symbol period. We also need to define RSS, which is the covariance matrix of the source symbol S, which is defined as expectation of S times S Hermitian, and because we have E of S is equal to 0. Using this, we put the constraint that trace of RSS is equal to MT. So, this is important. We are putting this particular constraint because we want total average energy constraint, because if you look at it, we take this particular expression when we have E of SS Hermitian over here, we basically get RSS, and if the trace of it is equal to MT, the total transmit power over here would be ES, because MT and MT would cancel out, and that would give the total transmit power. So, this is the signal model with which we proceed. Now, we will assume that H is known at the receiver. What does it mean? It means that the channel is estimated at the receiver and it is available, and again we will make the assumption there is perfect knowledge about the channel, this perfect channel estimation at the receiver. The Mimo channel capacity which we are talking about was given by a paper authored by Foschini in the year 96, and there was also work by Imre Telatar in 99, and there they discussed about this expression which is max of I between S and Y. So, between S and Y, it is the same expression over all possible distribution of the source symbol. So, the overall concept remains the same, but the things were derived in the papers by these people. So, IXY is of course the mutual information, and we know all the definitions now. So, it should not be difficult for us at this stage to work this out given whatever we have done in the previous lectures. So, this is the particular way which we have been expanding IXY, H of Y minus H. Okay, so, according to our definition, we should use a small h and not a capital H, indicating differential entropy, that means for continuous random variable. So y, so h of y given s, we have just derived this thing for AWGN, where we had seen that y given s is basically this whole thing given s. Now h is deterministic, h is known, so this is the random component at this point of time. So h of s given s is 0 and it is h of the noise given s. So basically what it leads us to is this particular one we could write as h of noise given s. Now again, since noise and symbols are independent, since these two are independent, we could write this as h of n, and this one would be h of y. So we have this expression which we derived for the CISO case. The expression at this stage looks similar. So in this case, if you see, h of n is defined, nobody can do anything with it because it's about the noise characteristics. All you can do is to work with h of y. And if you see the expression of capacity, it tells maximize this over all possible source distributions. So when you say in maximize I over all possible source distributions, what you basically do is try to maximize I over I of sy and maximize this expression where you can't do anything of h and n. So what you can do is maximize this expression. So to maximize this expression, we need to look at the details of it. So we begin with the covariance matrix of y, right. So covariance matrix of y is RYY, which is equal to E of YY Hermitian. So E of YY Hermitian, to get E of YY Hermitian, we have to look at this. So that means expectation of root over Es upon mt times Hs plus noise times root over Es upon mt and Hs plus noise Hermitian. So when I have a Hermitian, we could write it as root over Es by mt. I am just writing this part S Hermitian H Hermitian plus the noise Hermitian. So basically what you have is E of, if I take the product Es upon mt, because it's under square root sign, and you have H S S Hermitian H Hermitian. So that is the first product between this component and this component. That we have the next component plus root over Es upon mt H S noise Hermitian. That means this and this component is done. We have next this component root over Es upon mt times noise S Hermitian H Hermitian. Now we have the last component plus E of NN Hermitian. Sorry, we have NN Hermitian. So when we use the E operator inside, that means we bring the E operator inside, what you have is you bring E inside. So Es by mt would remain as it is. Since H is deterministic, E operates only on S. So H E S S Hermitian. Now you can see why we need the covariance matrix. Plus when I bring the E operation inside, E of S is 0, E of N is 0, so this term goes to 0. Again, E of N, S are both 0, so these are 0 and they are independent. So what we are left with is this E of NN Hermitian, right. So this is the variance. So we could write it in a more convenient form. H, instead of writing ESS Hermitian, we would write RSS H Hermitian plus this is the noise component. So N1 N2 dot dot up to NMR times N1 conjugate N2 conjugate up to NMR conjugate, expectation operator of this. So if you take this product, you will be getting N1 squared N2 squared up to NMR squared at the diagonal, rather mod squared, and the other terms would be cross terms, Ni Nj conjugate I not equals to j, and you are going to get expectation of these. So you are going to get expectation of these terms. So all these terms would be 0 because noise in independent branches are independent, and each of these would give the same value. So, it is basically n naught or n. So, what you have is basically n naught times I identity matrix, because all these would be 0 of size mr. So, we could as good as write this as n naught times I mr, right. So, we have our expression of ryy, and we now know how to write the expression of hy, and we also have the expression of hn. The expression of h of y, in that case we could write it as log 2 determinant of pi e r y y. So, we have changed a little bit over here. We have said pi e and brought it inside the determinant. This is as good as bringing pi e outside and raising it to the power of n, because determinant of a times a matrix is basically that a raised to the power of n times the dimension or the size of the matrix. So, this is no different equation, this is all the same, and h of n is log 2 determinant of pi e n naught I mr, and rather this is a little bit more convenient form of writing this. This is bits per second per hertz, you could write it in this way. So, I of s y, we could write it as hy minus hn. So, basically log this minus log of this. So, it is basically log base 2 determinant. So, if you look at the size of this is mr cross mr, this is also mr cross mr. So, basically pi e to the power of mr, pi e to the power of mr, they would cancel out. We would have determinant of r y y upon determinant of n naught I mr, right. So, r y y, let us expand it. So, I mr 1 1 would be log base 2, that is I, what we have here, yeah, we have over here es by mt h e h r s s h Hermitian plus this is n naught I mr, right, upon n naught I mr. So, what you have is basically determinant of this upon determinant of n naught I mr. So, this would lead to log base 2 determinant of I, because of this one, plus es by n mt, es by mt times n naught times h r s s h Hermitian. So, this would be expression of I x y. So, we could write the expression of capacity at this point, would write the expression of capacity at this point as capacity is equal to maximize log determinant of I mr plus es upon mt n naught times h r s s h Hermitian over all possible distributions of the source. That means, subject to the constraint trace of r s s is equal to mt. So, basically you are maximizing over r s s this particular expression. So, this would be the expression of capacity for the Mimo channel, and to derive this we have till now been able to explain the detailed characteristics of H, a typical Mimo channel. RSS we have defined, and we have discussed the typical model, which is for frequency flat, and we have also used the definition of or the differential entropy of the received signal, and we have derived that which particular entropy maximizes it. So, basically we have done step by step finally to arrive at this expression, and what it appears, if you would look at the few steps that we have taken, is pretty straightforward, given that we now understand all the exact terms that were defined in all previous lectures till now. So, we would like to conclude this particular lecture at this point, stating that we have arrived at the expression of capacity. I would like you to take a look at this expression of the Mimo channel capacity, which is very important, and based on this we will proceed on to carry out certain more expressions which would be able to give us a hint about what is the meaning of this particular expression. So, since we have arrived at the most important part of this course, which is talking about the capacity of the Mimo channel, and we have seen the expression, it now remains for us to explore this particular expression, open it up and see what happens when this when the channel state information, that is H, which we said is known, we say that let it be known only at the receiver. Then we will say that now let us change the assumption, and we say that there is a feedback channel. Because of the feedback channel, the channel is known at the transmitter. So, what extra can be done? What is the impact on capacity? We have also studied the correlation matrix or the correlation effect on the channel, or how can correlation be modeled. So, using whatever we have studied on the correlation model of Mimo channels, we will then bring out the impact of correlation on the capacity of Mimo channel. And finally, we will look at some architectures which will be giving us the capability to trade off between the diversity gain that can be achieved. We have analyzed diversity gain. We will see special multiplexing gain or the Mimo capacity gain, and we will see how can we trade off between achieving higher capacity and better error probability or a better reliability link towards the end of this particular course. Thank you.